Okay, so this record has started. Now the other will come. Okay. I have to tell you that I must tell you I have serious problems, but it should have, actually I should have talked about it. Serious problems is what to teach you. Now I have a task to change the syllabus, and well, it's challenging. You will see very soon why. Okay? And now I will see you. I have glasses. There are two syllabuses. One for Hungarian, one for you. There is significant difference between them. The order, the content and everything. Usually I prepared for the Hungarian syllabus and then I did your slides. Sorry for the quality of the new slides. Sometimes when it's too late, I just use the ChatGPT to translate, and it's not good at all. So when I upload them, I always improve them. And it's not. Oh, please no. Okay, great. Oh, I said open. So this is the talk for today. I don't have the intention to write on the board. So today is 9th of April. Tomorrow we will have a practice. The next week we will have a full week. And then the spring, the Easter holiday comes. Then, on 1st of May, we have national holiday. Wait. Oh, okay. So it's wrong. Okay, the situation is better. On 30th of April, we will have an additional class. On 7th of May, I would like to discuss you the homework and the practice. So we have 2.5 weeks to complete this semester. You can see Hungarian text there. It's not an accident. It's a copy and paste from the syllabus. I translate you. So there is orthogonal projection and best approximation, orthonormal basis, orthogonal matrices, fields above complex and finite bodies. This last sentence, this complex fields above complex and finite bodies, could be a full semester. That's a very, very long chapter. Then, singular value, singular vector decomposition, and the PCA, I don't know what is it, I cannot give you the shortcut right now, but it's also something very long stuff. Then the Hungarian, it's geometric order of reaction equation in chemistry. Great. Next one. The flexibility of matrix arithmetic task, linear programming task, so the feasibility of the solution of linear programming task. This MLF is similar to WTF. I have no clue what is it. Then, power of matrices, applications, linear recursion, power of incidence matrices, Graham-Smith orthogonalization that you have learned, LU decomposition, you have learned it, QR decomposition, Fourier series. The QR decomposition, do you remember Graham-Schmidt orthogonalization? Mm-hmm. You remember? When I did it, one task needed 45 minutes or something like this. The QR decomposition based on that. So this is a mess, and I decided the following. I will tell both of you, both means Hungarians and foreigners, this singular value, singular decomposition. I will tell you what is Fourier series, because that's good. And this QR decomposition is, I will not tell you, but at the very end, I will tell you this stoichiometric order of reaction equations, because the director of the Chemistry Institute sent me material. I cannot contact to the writer of this, and when we finish, you write a test and everything. That will be the new syllabus for the next one, for the next. There are a lot of things, and to teach this properly. Oh yes, and there is something else at the next page. That's funny. Further applications. Yes, this is really an informative and very useful topic. Further applications. Yes. Yeah. Okay. So I would teach you some minimum variance problem or something like this. Perhaps not you. 1 year later, to the next round, I will teach this. But so that's funny. So what I have, I've tried to tell you at least something. Perhaps if next year I do not repeat stuff, I will have more time, because I repeated a lot of stuff at the beginning of this semester from the previous semester. But this is a very, very, very long and complex material. I know that because I'm talking with the Hungarians, you will not use most of it. There will be a test. In the test, I'm pretty sure you will have LU decomposition. You will have also orthogonalization, perhaps something else. But I will compose and we write a test for, how can I say? I don't say easy, but it's normal. So you will practice and you will pass and you will get a good mark. At least that's my intention. Okay, I start the material and this will be funny. what is written, right? What has written here, I would need months to explain you. Really months. It's not 2 weeks. So let's start. There is a book. This note, is written in Hungarian. That's the problem. So it seems to be in the future I have to write an English notes or something like this. I don't know. The syllabus follows this book. Okay, let's start. Sum and direct sum of subspaces. Actually, long time ago, I defined what is sum and what is Minkowski sum of sets. And this is the same for subspaces. If you are interested in, you can check in the note in Hungarian. Properties of complementary subspaces. You can check in the note. I will not tell you this stuff. The main reason is not the time. The main reason is that it's not necessary for my purpose. Properties of the orthogonal. I forgot something and you didn't tell me. The other record. This obviously. Sorry. Okay, and I think okay, let's start. Not start. 1, 2, 3, 4. Oops. The recording is going right now. Stop. Okay, it has it works. I have the mic. Okay, so I start the recording here. I forgot to start in time. I just started to discuss the topics and what we will do in the near future, in the next 2 weeks. Okay. There was a definition also about direct sum. Great. Properties of the orthogonal complement subspace. That's also in the note. Orthogonal projection onto subspace, matrix projection onto a subspace, calculation of orthogonal projection, matrices of orthogonal projections, the best approximation theorem, vector notes. Okay, if I go back, this orthogonal projection and best approximation is here. I will tell you something from this, but not everything. This is too long. It's we don't have such time. Okay, there is this stuff that I will not mention at all. The decomposition of vector into components, optimal solution of a system of equations, linear and polynomial regression, linearizable regression models, projection onto a subspace, projection on properties of projection, equivalent definition of the projection. When is a projection orthogonal? This is long, so this is I would need months to explain. Okay, now something that is useful. Okay, we had vector space. That's okay, we also had basis previously. Basis just meant linear independent vectors, and you could write all vectors as the linear combination of those vectors. Do you remember this? It's like coordinate systems. It's okay. If the basis vectors are perpendicular, that's useful. Or the extension, the general term, generalization of perpendicularity is orthogonalization. Do you remember that you have two perpendicular vectors and you do the scalar product, then the result is 0. Do you remember this? We say that two vector is orthogonal if their scalar product is 0. In the normal life, in your science, in your work, in your studies, the two things means the same. But if you set to n-dimensional space or something bigger, then you can use the general definition. So what I got there, this blah 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 blah, it means you have basis vectors, and the basis vectors scalar product is 0. So then they are orthogonal. And we are dealing with this system right now. If you have an orthogonal system and the length of the vectors is one unit, I would say 1, okay? Then it's an orthonormal system. You remember the definition of normal vectors. So there is something that we call orthonormal basis, OB, and orthogonal basis, OB, and there is orthonormal basis, ONB. Okay? Let's go and continue this. No, I go back. Okay? Let's continue. You can define the independence of orthogonal vectors. It is in the notes. I didn't explain you what is the best approximation, but for orthonormal basis, you also can do this. Doesn't matter, it is in the notes, that is in Hungarian. You don't speak Hungarian, it doesn't matter. Which is important here? Orthogonal and semi-orthogonal matrix. real square matrix is called orthogonal if its column vectors or row vectors form an orthogonal system. So you divide into parts the matrix. All columns are 1, 1 vector, and these vectors form an orthonormal system, or its row. If your matrix is not a square matrix, then you talk about semi-orthogonal matrix. If you have a matrix, the matrix Q size is n times n, and you do the transpose, then and multiply with the original matrix, and you got the original, not the eigen matrix, then that's a semi-orthogonal matrix. If you don't, just a moment. So, this is an example for an orthogonal basis. If you do the multiplication, you always got 0. I mean the scalar multiplication. So Okay, the orthonormal for example could be many things, is many other. That's just a very well known example. If you do the multiplication, so these are about bases. What was the definition? If a matrix rows or columns are orthonormal, then the matrix is orthonormal. So for example, I do the opposite stuff. From this, this is an orthogonal matrix. Orthogonal matrix because if you divide this matrix to vectors, these columns, then you got that basis. That's an orthogonal basis.
Okay, but then I'm confused the difference between the orthogonal and the orthonormal basis because both of them the cross the scalar product is 0 for both of them. So I don't know the difference.
The big difference is the following. The length of this is 2, 3, 5. But normalization means the length is 0. So for this, for example, I can do the normalization. Then that's normal. Because the length is normal. The original definition was sorry. So the normal vector of A is the vector divided by the length of the vector. So if I write, for example, so that was the normalization. And if I choose, so the length here is 1. Because if you calculate the length of this, it's 41338, that's the length, and then you divide it. So the length is 1. And it direct somewhere, doesn't matter. It's okay? No, that's why I don't want to teach you so many things. So this is at the end of this class. We will reach, my analysis studies, and then physicists. Okay, sorry, I just forgot the original purpose of this stuff. So, here is the example. You can see the first matrix, that's 1, 1, 0. It's so the first matrix, that's 1, 1, 0. So if you can do a lot of things, you can divide this into vectors using the columns, because the definition allows you to use 0 vectors, null vectors. But the best thing, if you divide this into vectors from columns, so then you have okay, it's better if I write this way. This is one vector, this is another vector. The scalar product is 0. But this is not a square matrix, so this is not an orthogonal matrix, this is a semi-orthogonal matrix. problems. That will be interesting. Not for you, but for the Hungarians. So there are two vectors. And this is the same, so it's 0 again. So this is also an orthonormal basis. It's should be an orthogonal matrix, but because this is not a square matrix, it's semi-orthogonal. And the last, oh, I like it. Okay, let's try this, this, and this. Okay, we are lucky. So this is an wait. For haha, okay. This is orthonormal matrix because these are perpendicular, not perpendicular, orthogonal. And I didn't check, but this is a normalization. So if you calculate, so this is 4, 9, so 13, 36. So altogether it's 49, and square root is 7. So the length of all vectors is 1. Okay. It's great that we came here and didn't stay in the other room, because I thought I won't need to write anything on the board. Okay. This says the following: if a matrix multiplied by its transponent is the result is 0, then the matrix is orthogonal or semi-orthogonal. Okay, so I can erase this. I hope so. Here. This is my fate. That's good. Okay. So the statement says the following: if a matrix and its transponent, the matrix multiplication of a matrix, if a matrix transponent multiplied the matrix gives an eigen matrix, then it's orthonormal. Let's check this. Here, that's trivial. That's okay. But the transponent, sorry. You didn't tell me that sometimes I do write something and write something else. So that's why I'm not doing basketball, for example. I want to throw the ball and then something else happens. here it's another. Ow! Here. This is from there. And what is the transponent? Here it's the same. That's interesting. Actually, the transponent is the same. Yes. Okay, let's do the multiplication. 1, 0, 0. 0, 1, 0, 0, 0, 1. That's okay. Do you see? But here the transponent and the matrix are the same. Perhaps there, that's a different stuff. 0, 1, 0, 0, 0, 1, 1, 0, 0. What is the transponent? 0, 0, 0. This comes here, this comes here. This comes here, it goes here, here, here. You can see, so I do the mirror on the medial now. Okay, so let's do the multiplication. This this is 1, this is 0, this is 0. Uh, 0, 1, 0, 0, 0, and 1. So this is okay. This is also orthogonal matrix. Because, so what we have done, the Q, actually I should have done in the opposite order, but, so this is what we check here. But fortunately, I changed the order because this is a square matrix. It's not a problem. There, I have this A matrix, and let's start with the okay, here is A matrix, 0, 1, 1, 1, 0, 0, 0, 1, and I need its transpose. This is 0, this is 0, this is 0, this is 1, this is 0, 0, and 0, 1. So this is the Q, and this is the transpose. I also. It's okay, and it's okay. Okay, so I do the multiplication. Zero. Wait. Take. Okay, I can do it actually. No. Wait. M. Okay, I think that here the opposite should be written. And then that's 1, that's 0, that's 0, and that's 1. And this is A2. So this is also an orthogonal matrix. Okay, here. B. I finish this and then, okay, so the B, no. I want to write So I, using these trigonometric equations, I also got this. And we don't have time for CE. I will continue tomorrow. This one, let me see what we could do today, very quickly. So we went through the orthogonal matrices, and this is the, yeah. Oh my God. Okay, so we reach this orthogonal matrices. Ooh. Okay, thank you very much. Did you understand?
Yeah.
Okay. This is very simplified right now. Very, very simplified. Because we don't have time to do everything. This is I stop this.